Hello everyone, I'm Xudong Liao from Hong Kong University of Science and Technology, and today I will be presenting our work entitled Pallas towards optimal rack scales, microsecond-level CPU scheduling through in-network workload shaping. This is a joint work with collaborators from USTC, Peking University, and Inspur. Let's get started. Microsecond scale services are now common in data centers, such as workloads of in-memory key-value stores, searching rankings, and function as a service. These services require very tight tail latency service level objectives, often tens to hundreds of microseconds, which are critical for user-faced experiences. To meet these demands, recent data center operation systems such as X, ZigOS, Xinchen, and Persephone has introduced several data plan designs with kernel bypass networking and lightweight scheduling. These systems are optimized for low latency scheduling within a single server. However, with the increasing demands, many microsecond scale services now span multiple servers within a rack, and then the scheduling becomes more challenging. This brings us to a central question: how can we efficiently schedule the microsecond scale workloads at rack scale? Existing representative rack scale schedulers like RackSched follow a two-level approach. The first one is inter-server scheduler. In a TOR switch, use a JSQ-based method to assign requests to each server based on the queue length. Then each server uses intra-server scheduler, such as centralized first-come, first-serve in ZigOS, time sharing in Xinchen, or core partition in Persephone to assign requests to CPU cores. However, this design suffers from two critical problems that hurt tail latency. First, JSQ-based load balancing is application agnostic, so it does not account for how much CPU time each request will consume. So even if two servers have similar queue lengths, their actual load may be very different. Furthermore, due to microsecond scale dynamics, the queue length is hard to estimate, which is prone to steal information from the network RTT. Second, the intra-server scheduling must deal with a mix of long and short requests. This suffers from head-up-line blocking, where short requests wait behind the long ones. Even advanced intra-server schedulers struggle to mitigate this. We investigate this issue with the following experiments. We use RackSched, the JSQ-based load balancing, and evaluate several intra-server scheduling used bimodal workloads with a short and long requests. We can compare centralized first-come, first-serve, time sharing, and dark, which are practical schedulers, against the ideal case process sharing. As the ratio of short requests increase, we find that all practical schedulers perform much worse than ideal, with up to 50 times tail latency slowdown. This shows that the head-of-line blocking is hard to avoid when long and short requests are mixed. But here is a key observation. When the workload is purely homogeneous, either all short or all long, all schedulers perform very close to the ideal. So this leads to a key insight from the previous experiment that suggests a new direction. What if we could proactively make the workload homogeneous before it reaches the servers? This brings us to application-aware scheduling. It explicitly split the request into different groups and schedule them in different subsets of servers. And today, we believe there are multiple opportunities to make this work. First, in many applications, the request type is visible in the packet header and strongly correlates with the CPU cost. For example, in RackSched, get requests are short while scans are relatively long, and this can be distinguished by the key range and operation code. Besides, programmer switches are now available in modern data centers. These switches can classify packets and enforce customer scheduling policies and line rates. These opportunities together enable a new possibility. We can now categorize and schedule requests directly within a network, paving the way for rack-scale application-aware scheduling. This leads to the design of Pallas. Its core is to shaping the workload proactively within the network. At the TOR switch, we classify incoming requests into multiple groups based on the expected CPU cost. Requests in the same group have similar cost, which give us the workload homogeneity. For each group within one intra-group load balancing use accurate load estimates, such as the outstanding request numbers. This ensures that each group's traffic is distributed evenly across the assigned servers. Finally, on the server side, because the incoming workloads is now uniform, we can use simple yet optimal intra-server scheduling, such as the centralized first-come, first-serve for the homogeneous workloads. This setup fundamentally eliminates the head-of-line blocking and allows the scheduler to operate near the optimal. Note that most servers only need to handle one group, making the entire rack operate as it were scheduling the homogeneous workload. For the servers facing mixed ones, we use core partition algorithm in dark. Please refer to the optimality analysis in the paper. Well, the Pallas design looks simple, making it work effectively as a system brings several challenges. The first one is how do we efficiently shape the workloads? Having more groups give better homogeneity and better scheduling outcome, but may sacrifice resource efficiency. We need to find the right balance between the workload homogeneity and the resource efficiency. The second one is that how do we handle long-term workload changes? Because the request distributions can shift over time. For example, the ratio of get or scan may change over time. Simply replacing the scheduling policy would cause disruption. So we need a mechanism that adapts the policy smoothly and incrementally. The last one is how to mitigate the short-term workload bursts. Microsecond scale services often experience transient burst spikes. A coarse-grained control mechanism may be too slow to react. To this end, we need a lightweight, low-latency burst handling mechanism within the data path that does not introduce the overhead or instability. So to address the first challenge and shape the workload effectively, Pallas generated workload shaping policies in the following steps. The first one is to find grouping policies. We use a clustering method to analyze the request execution time and divide the request into a small number of homogeneous groups. The second one is to select the best policy from multiple candidates. We use empirical simulation-based profiling to evaluate how each grouping policies perform under the expected traffic. This helps us to pick configurations that balance the performance and the efficiency. The next step is to provision resources and generate the actual scheduling logic. For each group, we assign CPU cores with respect to the expected load and generate the intra-group load balancing with weights and configure the simple intra-server schedule in algorithms like centralized first-come, first-serve or dark. The resulting policy is then enforced across the switch and the servers. To handle these long-term workload changes, Pallas introduced a lightweight policy adaptation mechanism. We continuously monitor the actual CPU usage of each group and compare it with the provisioned resources. If a huge mismatch is detected, for example, a group consistently consumes more or less than the allocate resources which exists a predefined threshold, we just update the policy. Importantly, we only update the mismatch groups, keeping the rest untouched, which minimizes the disruption and avoids the cost of the full policy regeneration. During this transition process, if a server receives short requests from the new group, we use request bouncing to redirect long requests to the right destination. This approach allows Pallas to adapt to long-term workload shifts gracefully and incrementally by resolving a potential head-of-line blocking during the transition process. The short-term bursts are also common in the microsecond scale services. These sudden spikes can overload a group for just a few milliseconds. To mitigate this, Pallas use a best effort conditional request cloning mechanism. When the switch detects a group is overloaded based on the request rate, it selectively clone the request to other underutilized groups. However, if the cloned request reach an underload server, it will get processed normally. But if not, it will be safely dropped without impact. This makes this mechanism low regret, which means that the cloned request only give positive feedback, but never makes the performance much worse. Here is the overview, high-level overview of the 4 Pallas system. First, the request enter the shape, enter the rack through the T1 switch, where Pallas classifies them, shape them into homogeneous groups, and balance them across servers. On the back end, servers run simple schedulers to process the uniform workloads. In parallel, the control plans continuously monitor the execution statistics and updates the shipping policies when needed. In addition, the burst handler clones requests to backup groups when transient overload are detected within a data path. This closed loop designs allow Pallas to dynamically shape the workloads and schedule the workloads at line rate. Pallas were implemented on real hardware testbed. The switch data plan is programmed in P4 to perform workload shaping, group-based load balancing, and burst detection. The control plan enforces policies and handle workload monitoring and adaptation. On the server side, we just use simple schedulers as discussed in the previous slides with centralized first-come, first-serve or dark. For the experiments, we used a Pheno switch with 10 servers. We evaluate Pallas under synthetic workloads, including the binomial ones and multimodal distributions, and real-world applications with RackSched. For the synthetic workloads, we observe that Pallas significantly reduces the 99th percentile latency and improves the sustainable throughput by up to 2.1 times under 100 microsecond service level objective. This is because that most servers in Pallas handle only homogeneous workloads, allowing them to use simple schedulers with near-optimal performance. We also evaluate Pallas using a real-world application RackSched with get and scan requests. In the normal bimodal case, 90% of the requests are short get requests, and the remaining 10% are long scans. In the poor bimodal cases, the mix is 50 to 50, which stresses the scheduler even more. Compared to the RackSched plus darker solution, Pallas reduces the tail latency up to 5.5 times. This is because Pallas can classify these requests at a switch, separate them into groups, and ensure the server does not mix long and short requests. These results show that Pallas is effective not only in synthetic benchmarks, but also is useful in the real applications with complex request patterns. We also evaluate Pallas to show how it reacts to the long-term workload changes. We start by a port bimodal workload with 50% get and scan, then shift them to a normal bimodal workload with 90% of get and 10% of scan. As you can see, the get request tail latency remains stable and the scan latency adjusts smoothly. This demonstrates that the ability of Pallas to gracefully adapt to changing workloads without global reconfiguration or performance spikes. Our lightweight monitoring and partial policy updates make the system robust to shift over time. We also compare Pallas with other RackSched scheduling methods. As shown here, Pallas consistently outperforms other alternatives in terms of the tail latency and the sustainable throughput. Besides, we show that the scalability of Pallas is increasing. By increasing the number of servers, Pallas show near linear scalability, maintain low tail latency, while increasing the throughput with more machines. This confirms that Pallas is practical for real-world deployment at rack scale and beyond. Please see more results in the paper. To recap, Pallas is an application-aware rack scale CPU scheduler for microsecond scale workloads. Its core idea is to proactively transform mixed workloads into the homogeneous ones within the network with programmable switch. This enables simple yet near-optimal scheduling and load balancing across the rack. Besides, this makes the system simple to deploy, where the most logic runs only in the TOR switch, and the servers maintain simple logic with lightweight and near-optimal schedulers. Our evaluation on Pallas showed significant improvements in the tail latency and throughput. Pallas is open source and available at this GitHub link. Thank you. I'm happy to take any questions.